Good afternoon, guys. Jonathan, yours really good. I love the information, the hamster. Not going to do that when I get back to London. Santorini doesn't have any beaches. I didn't know that. I was just talking to my wife saying we should come here for some holidays. But this is great. So today I'm going to be maybe focusing on one aspect of what I think is very important, and that's memory. I think everyone has been focusing for the past 5 months now on reasoning, but I think fundamentally, memory is what really makes everything work. So I'll kick off with this. I'll give a prize to whoever knows what Titan this is. Shout. Prometheus, that's good. The prize was going to be money because I thought no one was going to get it, but I'm so glad. The prize is not money. Yes, Prometheus. And he created man, and he also gave man fire, which we can say fire contributed to a lot of the good things we have today, mostly a lot of the development we have in civilization. But then it goes on to get punished for it for eternity, and the story goes on. But the key thing is today, I am going to not give you fire, I'm not a Titan, but I'm going to essentially share with you ideas that I think is the equivalent to us giving fire to AI, and that's memory. So, does anyone know who this is? Yep, excellent. So, me and Andrew did a course last year focused on RAG and Agentic Systems and all the good stuff. But before we did about 2 hours of filming, Andrew asked me a very, very interesting question. He says, hey, Richmond, how do you model memory? Because he realized, and still does, that memory is the fundamental thing that we need to get right to be able to build AI, AGI, SSI, whatever thing comes next. So, the question, how do you model memory? And I've been thinking about this ever since he asked me, so I don't have the ideal answer yet, but I'm getting a bit closer. 08023188077. That number is the first mobile number I ever had when I was 10. That was 20 years ago. And I remember that exact number till today. And I'm sure there are numbers like that you guys remember as well. Anyone wants to shout out the first phone number, if they can remember it? Go on. Is that no one can remember the first phone number? The first and the last number is what you can remember. It's still good. Maybe I have incredible memory. But long story short, humans have very good memory. Very, very good memory. So today we're going to be talking about why memory matters. We're going to be talking about AI memory, which I think is a backbone and should be the backbone of intelligent agents. We're going to be talking about the core components of memory management. We're also going to be talking about each of these components of memory management and the role of databases in the future of AI, and we can have some fun about predicting the future. So, why does memory matter? Because it allows us to remember phone numbers. It allows us to remember a bunch of information that we need, and I'm talking about humans. Memory matters because it allows us to be more efficient, reliable, and performant humans, right? The smartest people I know can recall information pretty well, and that makes them very good at their various roles and jobs. So that's a human brain, half of it. It will make sense later at the end of this presentation why we only have half. But humans have different forms of memory. So memory isn't just one thing. It's a bunch of things. So the first one here is short-term memory. So I can tell you some information right now, then you might remember it, but maybe after this talk, you might not remember it. That's short-term memory. Then there's long-term memory, which is like my phone number, the one I remembered from 20 years ago. Then we have working memory. This is a form of short-term memory where you use information that you get to enhance the information that you have previously to be able to answer information or to be able to answer questions in real time. Then you have episodic memory that are associated with events. Then you have semantic memory that are associated with meanings and all of the good stuff. So if I tell you to think of the color red, maybe you're thinking of blood, maybe you're thinking of roses, semantic memory. Then we have genetic memory. Yes, there's genetic memory, right? So your body remembers what to make your eye color, right? That's in your DNA. So we have a lot of different memories. Humans, memory is not just one thing, it's a bunch of things. So I started thinking, how can we make AI agents work the way we want, in a similar way humans does? Because that's the whole promise of AI. That's the whole point. We're trying to create a computational entity that mimics human intelligence and surpasses it. So if we want to create something like us, we should look to us as well and see what works. And memory works. So why memory matters in AI agents? Why does it matter? We need AI agents to be reliable. We want AI agents to be able to take in information, then after maybe 20 turns of us giving it prompt, it giving us an answer, it's able to remember earlier aspects of our conversation. It makes them reliable. We want agents to be able not to contradict themselves. We want them to understand what we're saying, what we mean, and we want to be able to trust the AI to complete a task. Memory has a key part. We want AI agents or AI in general to be believable, right? I think maybe 2-3 years ago, if you were talking to an AI, you'd be able to know you were talking to an AI. But now, it's sometimes hard to tell. But still, memory has a role to play in making agents believable and making them capable. Memory, when done properly within AI agents, enables them to have access or be capable of different functionality. Multi-hop reasoning, right? They can then take in information that they had previously and use that to inform new actions. It makes them more capable of different tasks. So what they need is consistency. They need recall, the ability to remember information from previous interaction, continuity, to be able to carry on conversations and keep going based on previous information, reasoning, continuous learning, personality. So all of this is AI memory. The key thing I want you to take away is memory is the foundation of intelligence. It's not just a feature. So in a lot of, I'm going to get a bit technical here, in a lot of frameworks, memory is implemented as maybe you want it, maybe you don't. You can add like maybe you want to, OpenAI brought out the SDK 2 days ago or yesterday. The time is a bit muddled up in my head, but they have a feature where you can add in your vector store. It's an option. I believe memory shouldn't be an option. Memory is a necessity. It's the foundation of intelligence. So, AI memory. We understand memory from a human perspective. Now we want to talk about AI memory because we're trying to make AI agents like us. So we need to look to us to build efficient, reliable, capable, believable AI agents. Looks like there's a lot going on here, but I want you to focus on this part. It's missing a memory module. This is a common interaction that you can have with any LLM. You give it like an input, the input goes into the context window, then the LLM is able to generate an output and give you a response. That, if it's missing some form of memory module, is not efficient. It doesn't remember information from several sequential turns of conversation, right? So you tell it your name, it gives you an answer. You ask it, hey, what was my name? It's not going to be able to remember it without having some form of memory. Or at least if the context window is it's refreshed and you start a new chat. But probably in a lot of talks, a lot of people have spoken about vector databases. That is memory. That is a form of memory, but it's not the final stop. Like I said, memory is several things. It's multiple things. So vector databases is a step in the right direction. And over at MongoDB, we actually have features that allows you to store vector data within MongoDB database. We have our customers using MongoDB as the operational database and the vector database. So we understand how people are using vector database to augment memory within the agentic system and the AI system. So we understand it's not enough. There needs to be more, that people need more. So, what are the limitations? We found that the embedding quality matter. And what I mean is, whenever you're using a vector database, you have your images, video, audio, text, you take the objects, you pass it through an embedding model, and what that does, it turns it into a set of numerical, turns it into a numerical representation, which is a vector, which is like an array with numbers of different position types, data types. So sometimes, or most of the times, the embedding quality is not good enough. Also, the retrieval relevance, it changes, right? You have challenges with retrieval. The context window has a limitation. Because you have a vector database doesn't mean you've extended the context window of the LLM itself. And also, we see that there is no reasoning over memory. There is reasoning in the information passed to the LLM, but there's no reasoning over the actual memory itself. So there are other issues that we've seen. Let's talk about solutions. But before we go there, let's talk about what we need. So we need persistence. We need relevance. We need evolution and adaptation. We need organization, and we need integration. We need AI memory. I hope I've made a compelling case here. So let's define it. So I'm going to say it again. AI memory is not just one thing. It's a bunch of things. It's a bunch of things, for humans anyway. So which means that AI memory is kind of like a system, is a mechanism of different components working together to ideally store information, retrieve information, and evolve information, right? I've kept it in a better, I've said it better here. But really, we have to start thinking about the different forms of memories that we have as humans and seeing how we can augment that or implement that within AI. So long-term memory, short-term memory, semantic memory, procedural memory, episodic, working memory, all the different memories that we have. How can we bring that into a system and make the AI system work better? So that's what we're going to be looking at today. And there might be a lot going on here, but the key thing I want you to focus on is this area, which is the memory management, because even though I'm talking about AI memory, the key thing that actually works is the management of memory. Is how do you, and it's not a solved problem, which is the main question, how do you model memory, right? So if memory is not just one thing, then how do you bring the different things together to make it work? This will make sense to you by the end of this talk. So let's talk about the core components of memory management. We know there's AI memory. We kind of defined it. And we know it's not one thing. It's a multiple of things working together to create some form of highly reliable, believable, and capable AI system. And we know that we need some form of management of it. But what are the core components? I'm going to take a step back. We know CRUD, right? CRUD is create, read, update, delete. We've done it very well for several years within database, within information retrieval. But when we start going into the realm of memory, and when I started to think about it, I realized that there were several other components that we have to actually implement within a management system. And Jonathan mentioned the project AI Ops from Microsoft, and they had this coordinate module. That is memory management. That is the aspect of that framework that manages the different modules, right? It's important. It's not just Microsoft trying to solve this problem. People at Stanford and other research labs are trying to solve the memory problem. And this is in research now, but over the next coming months, because the space moves very quickly, over the next coming months, we're going to see an emergence of frameworks, of platforms that are solving memory. So these are the core components. They're all going to make sense to you by the end of this. Initialization, segmentation, structure, creation, retrieval, update, deletion. So initialization. How are you starting your memory? How are you starting your agent with information? So when you click new chat on ChatGPT, there is no specific memory. It doesn't have any initialization procedure, but that's a lie. It does. There is a feature in the settings on ChatGPT where you can put in the ways you want it to respond. So it does have the initialization. That is a form of initialization. You can have a blank slate initialization approach where you have nothing. The agent knows nothing. There is no memory. It forms its memory from when you're interacting with it. So there are different initialization methods. We're going to talk about that in a bit. Then there's segmentation. How do you structure memory, right? How do you begin to look at the data you're getting, the information that's coming in? Then how do you begin to divide the information up? How do you begin to create structures that enables the agent to think about the information in an intuitive manner? That's where you start getting into the conversations around graph, right? Knowledge graphs, or maybe nested documents and nested attributes. So that's segmentation. Then there is structure. Now, segmentation and structure are going to sound similar, but the key difference is we are trying to get that threw me off. Let me come back in. So there is a structure. In structure, we are trying to understand not just how we segment the memory, but each memory units that we've created, we want to understand how we can link them to another memory unit, right? So a paper that does this, I'm going to reference a bunch of papers here. It's called AMEM, Agentic Workflow Memory, and it does this by creating it's just an attribute within the memory units that it generates that links to another memory unit. You're trying to create relationship between memory units. Another way you can create structure is just chronological, right? Just time, sequential. So each of the memory units can have a timestamp. We'll talk about structure later. Now there's creation. How do we start to create new memories? So there are different ways you can approach this, right? So I'm gonna talk about humans again. So when do we create new memories? We create new memories when we experience things, right? Then there are times when we go to sleep. Well, everyone goes to sleep. I assume everyone sleeps. So we go to sleep, we dream, and when we're dreaming, I'm not a neuroscientist, I don't know how the brain works, but very loosely, I know that our brain is actually reflecting on the experiences of the day and trying to take the most important bits and turn that into memory and enable for us to recall it. You can implement that mechanism in AI today, in AI agents, right? You can create your system and implement an ability for them to reflect on the action of the day if you're storing them as logs, and then summarize and pick out important bits and use that as new memory units. You can generalize, you can summarize. So the different strategy to creation. Then there's retrieval. You've heard of retrieval a lot of times today. So you can retrieve through semantics, that would be vector search. You can retrieve through text search. You could retrieve through graph, right? Through relationships. So that would be a graph traversal. Then you update. Now this part is the most crucial bit. How do you update memory units within your system? It's very hard. We don't even understand how humans update memory, right? We don't understand how we keep how the brain works fully, but we can infer some mechanisms on how we can update the memory. So one thing I saw in a bunch of papers is there was in a paper generative agents. One way that they were updating memory is by keeping a score, think of it as like a weight for each memory units, and whenever the memory was retrieved, there was a change within the factors of the units, which are relevance, importance, and recency. So you can update memories based on those factors. Then deletion. Human beings forget. And I was having a debate or conversation, which is, why do we forget? Is it a feature? Is it a bug? Is it on purpose? To me, it feels like forgetting feels like a bug. Right? If you have a system that forgets the information you give it, it's not a good system. So I'm not going to get philosophical here, but why do humans forget? Think about that. If you have an answer, let me know. Maybe our bandwidth is too small and you have to forget some information. But sometimes humans never truly forget, right? There's some memories that you have in your subconscious that you didn't even know that you remembered, and suddenly something in your environment triggers it. So the human memory is very, very interesting, and I believe it can help us build truly intelligent agents. But deletion, I don't really mean delete, because data and storage itself is commoditized, it's cheap. We can actually store terabytes of information at a relatively cheap cost. The reason why we want our agents to forget is because having too much information is also a bad thing, right? It pollutes your context window. It makes your agent or your AI not give you the right answer. So there needs to be some form of forgetting mechanism within your memory management system. So this is what I came up with. It's CRUD. This is the framework that I'm suggesting, or I'm trying to give to you. Think of this as the file, I guess, that we're trying to give AI to be able to create efficient memory management systems to effectively be believable, reliable, and capable. So, as I was creating the presentation for this talk, I was thinking, is a new role going to emerge if memory is the thing? Are we going to see some AI memory engineers? If that becomes a thing, you heard it here first. So back to this image. So over here now, this part probably makes a lot of sense because we have the initialization, we have the segmentation, we have the retrieval, update, creation, delete, and structure is missing because I forgot to put it in this diagram. But really, this is the management system, the memory management system that we are trying to create to make our agents, to improve their reliability, believability, and capability. So this is what I'm proposing, ISCROD, the framework for memory management. So let's go a bit deeper. Initialization. When you build your agent, what initial memory are you going to give them at time zero, right? Within the life cycle. At t equals 0, what do you want the agent to know? So sometimes we see a lot of people giving a knowledge base, right? So you have a bunch of data in your private data. You can connect your agent to this. So your agent is aware of it at the start of the conversation, at T0. Sometimes we see people giving their agents personas, right? So they tell the agent, I want you to behave like an angry person, and then every time you respond angrily and negatively. So you're giving your agent a persona at time 0. So when you say hi, the agent will tell you, go away, because he's got the persona of an angry person. So I try to remember persona. I have an acronym, SEED, which is slate, which is blank slate. Then E is engineered data structure. The other E is for external database, and D is for design persona. So SEED is the way I try to remember the 4 ways that I've seen some of the researchers are initializing their agents. So I'll go over them again. Blank slate initialization. So your agent is essentially starting from fresh. It knows nothing. So it's going to gain its behavior, and it's going to create its memory from the interaction that it has with the system user. And there are a few papers that take this approach to actually initializing memory. MemGPT, Memory Bank, and that says Mayu MN, but it's actually my agent understands me. It was just too long of a title to put on a diagram. Then preloaded persona. So another paper that does this is generative agents from some researchers at Stanford. Before the agent gets to interact with humans or any other agents, the agents are given a persona. They're told what they like, what they don't like, what they behave like, what their characteristics are. So this is usually good if you want your agents to be believable. Then you have the structured data bootstrapping. So this essentially is you're starting your agent with not just data, but data that is organized in a way that allows it to infer association at the very beginning. So we see this in AMEM and HippoRag. And HippoRag just brought out, HippoRag 2 came out a few days ago. So external knowledge augmentation is the popular one, is where you just have an external repository and you just connect that to your LLM or to your agent at the start. It's the easy one, and it's the one that provides a lot of value. But there is not one size. There is not a silver bullet. You can actually mix and match some of these approaches. Segmentation, dividing memory into specialized units. So the 3 T's of segmentation: temporal, tiered, task. I want you to imagine having a bunch of data coming into your system. How do you want to segment the information, right? When the data is coming in, how do you want to organize it? So some people use time to organize it. So when you're talking to ChatGPT, I don't work in OpenAI, but I'm sure each of the interactions are timestamped. And from there, you can have a mechanism that can have information that are maybe information within a certain time that's passed, stored in a more long-term memory, then more recent information in short-term memory. That can affect the retrieval. Then you have tiered segmentation. Now, this one is just replicating some of what we understand in humans, and we're trying to bring this to these computational systems, right? So working memory, episodic memory, and semantic memory. So semantic is easy, so these are facts, and these are facts about the world. You can think about this as just knowledge. Now, how you retrieve them is a different story, but semantic is essentially knowledge of the world. Episodic are events, memory from events that are occurring. And procedural are an understanding of how a task is to be done sequentially, step by step. Then we have task-based segmentation. These are where you're separating the memory based on the type of classification in terms of work to be done you're giving it. So that's segmentation. Then we go into structure. We've seen a bunch of folks actually structure, take an easy way out, essentially, by structuring the data or the memory as just a bunch of just logs. You're just storing it as text data, just storing it as logs. That's very easy to do. You can think of maybe your conversation, you store it as logs and store it in your database. But then you could get a bit creative and go into graph structure, right? This would be, you get your data in and you store in your memory into some form of graph. Or you can even extend it to hierarchical and workflow structures. So that's very quickly structure, creation. How do you create new memories? So I touched on this previously, but creating new memories from the information you have from interaction is an important aspect of memory management. Reflection. we've seen that in some of these memory architectures from research, the creation of new memories is done as a background task. You set a cron job, so maybe at the end of the day, they have the agents reflect on what's occurred and start to generate new memory and then store that in a database. Then we have summarization, summarize what's happened, and just store that, maybe remove all the informations that are not useful, create a more compact summary of the day, and store that as well. Then you can have generalization, look for patterns across certain tasks, and store the patterns and use that for future tasks that you're given. So there are different ways we can create different type of memories, and you can implement all of this ways. But we've also seen other more specialized ways of creating memory. Workflow induction. So this is, you have a set of tasks, right? With agents, we have the chain of thought prompt techniques being used in a lot of LLMs today that allows them to extend the reasoning capability and take a task and decompose it into several different tasks. Now, we can actually store those several different tasks in memory and use them for future tasks and record it all successful or not. Then we have this alignment, right? We're creating a bunch of new memories, maybe learned from the prompt, or also learned from the interaction. Retrieval, and this is the fun bit. This is where I get to have a lot of fun. Embedding is very simple, right? It's simple because now we've done it a lot. There's a lot of companies that have come out to solve embedding. But how you retrieve memory, how you recall memory is important to make an AI agent work. The same way from 20 years, I can recall the phone number that I had, one of my first phone numbers. It would be a very efficient AI system is one that you can go in and probably ask it some information from that you've given it maybe 2 weeks ago or 3 weeks ago, and it's able to use that to inform the current interaction. That's an effective system. So we can do that. We have vector search, right? We have embedding-based vector search. A lot of databases do that. We do it at MongoDB, and we do it very well. But in research, we see a lot of memory architectures proposal using embeddings to inform the memory management. But not just using embeddings. Some are using multi-factor scoring system. So they're using a combination of attributes from the memory units to inform how the memory unit is recalled. So you're not just going to recall when you're doing RAG based on semantics. You want to recall based on the importance of the memory unit to the actual context. Or you want to recall based on the recency. So how recent the memory unit is probably more important than a memory unit that was maybe captured 2 years ago. So this is just going beyond retrieval from semantics. Then we've also seen people use the LLM itself trigger memory retrieval. So you give the LLM a bunch of tools, and you just let it choose when it wants to use the tools to retrieve memory. So you're just telling the LLM, use this recall mechanisms whenever you want to. So there are other ways that we've seen people retrieve memory units. We've seen people use graph, and we've seen people use human-like memory model, which is you take a sort of like a human-centric approach to recalling memory, in where you actually have your memory units, but you're thinking about adding thresholds to your memory, to your recall mechanism. So these are different ways that we've seen people try to retrieve memory from their memory management system. Then updating. Updating is another important aspect, is how do we start to change existing memory within our system based on new information. It's not an easy task to do. One that there is not one solution, but another conversation I was having with a teammate is, should agents be allowed to modify previous memory based on new information, or do you just create a new memory unit and then reference the change. I think Jonathan spoke about that in his talk as well. But we really need to think about how do we want memory to evolve when we're getting new information, and that happens through having an update mechanisms. A simple and easy way out is just whenever you get a new event, you just store it within your database, and then your agent can then retrieve any new information. Or you can go a bit advanced and start refining the existing memory. You start changing the memory within your database based on new information. So for example, I tell an AI agent, my name is Richmond. It says, okay, stores it in its memory, your name is Richmond. I said, okay, I made a mistake, my name is John. It then changes the original memory unit and changes it from Richmond to John. My name is not John, my name is Richmond. But that is what refining existing memory looks like. Now, should an agent be able to do that, or rather should we just store a new memory unit and reference a previous one? There are different approaches to this. Then state changes over time. So we can have rules that are inferred from interaction, and we can start to use new information to change the persona of the memory of the agent itself. So these are sort of like changing its fundamental memory basis. There are more ways we can update. So you can actually implement a strength modulation mechanism where when new information comes in, you have certain attributes that you can increase the weight you've assigned to it. So if you see that a memory unit gets called in several times within the context, you can start to increase the importance of that memory unit to the information. So you can start to strengthen the signals that you're using for your memory recall. Then you can also have graph-based updates, right? If you change one information here, it starts to cascade down to other memory units and start to update the information. Then you can also have continuous prompt learning as well. So the last one is deletion. And do humans, we forget, but we want our AI system to actually delete memory. Storing information and data is cheap. So no, we don't truly want our systems to actually delete memory, but we want a way to reduce the importance, the signals of different memory units so they're not recorded every time. So there are code storage as well. There is the concept of code storage. But yeah, so we can go into pruning memory, just removing a bunch of memories that are not required. And sometimes we've seen folks that summarize memory units that they don't need. They just summarize it to make it smaller and store that maybe in some form of long-term memory. So we also have some form of forgetting, right? Now, this is going to happen naturally if you have a multi-factor signals within a memory unit. So when you start reducing the importance of a memory unit, ideally your system is just going to forget and not recall it ever again. Then you have selective memory retention. So you want your LLM to decide when any information is important and only select those information, and the rest are just are thrown away. There are other aspects of deletion that we've seen. So you can just archive memory. You don't need to delete it. You can put memory in cold storage or some online archive that you can then implement a retrieval mechanism that can get a certain memory from cold storage based on some form of event. Well, we also have decay-based forgetting, which is quite similar to maybe relevance-based forgetting. Then we have knowledge graph pruning, which is similar to short-term pruning, but this basically means when you prune, when you actually forget the initial memory, it then cascades to delete or forget the rest of the other memory in the system. So what role do database have to play? I spoke about a bunch of techniques, right, in the ISCROD framework. They sound complicated. A lot of it is still in research. There's a bunch of research papers and researchers trying to solve the AI memory problem and memory management. What role do database have to play in memory management? Databases have a fundamental and a foundational role to play, because in all of what I just mentioned, the database you're using for an AI system enables them. So you want a database that essentially where you can store different forms of data, right? And you also want a database that can allow you to have different form of retrieval mechanism, right? Graph traversal, vector search, text search, time-based search, geospatial, because there is no one way to retrieve memory. There are several ways. It's a mechanism. So, MongoDB, we are very focused and have been focused on how we retrieve information from database system for several years. So MongoDB we're a developer data platform, and we have a bunch of features, and what we're known for is our database. It's a NoSQL database that allows the storing of JSON-like data, right? JSON format. It's based on the BSON data model. It's powerful, universal. Most people have heard of MongoDB. And today, a lot of customers are using the MongoDB database with its vector search capabilities to power the AI application. We spoke about different search mechanism, and full text search is what most people are used to. Vector search for the last 3 years has become very popular with RAG. Hybrid search, if you've not heard, is basically a combination of full text search and vector search just to improve the recall and the retrieval accuracy of your system. MongoDB enables all of this through its features. We have the MongoDB Atlas search, which enables all the full text search, also fuzzy matching as well. Atlas vector search, which allows you to actually search for through your vector embeddings. And then we have the MongoDB query language, and I put this there for a very good reason, and that is the MQL, the MongoDB query language, allows you to start to build all of what we just spoke about. All of the mechanisms of transforming data or adding weights to memory units, those are capable and made easy from the MongoDB query language. So the course that we created with Andrew Ng and his team last year, April, it shows some examples of how you can add boosting to some to the retrieval of your of memory or data in your system. That's just one step towards actually creating a memory management system. It looks like there's a lot of things going on, but I'll just touch on a few things. To some of our advanced customers, they are understanding MongoDB as the memory provider for agentic systems, right? That begins to make a lot of sense if you start to think about how crucial memory is to making human work, and then how crucial memory will be to making AI agents work. So the question still remains, and I'm still trying to figure out the answer. So when I bump into Andrew again, I can say, hey, we figured it out. We created this. Check it out. How do you model memory? The presentation here is not in the right way, but we remember what we started with earlier is the way humans actually the different ways humans have, we've actually informed our memory system, right? The way our memory actually works, the different types of memory we have. We can implement different, similar versions of that within computational system today. We have the tools. It's just how you model it, how you get it to work together. The management system is what really allows you to build those reliable, capable, and believable AI systems. So, short-term memory is basically the context window. Long-term memory, that could be your knowledge base. Then working memory, I worked with a company called Tavily, and we created something called hybrid RAG to simulate working memory. Episodic memory could just be user interaction logs that are time-stamped. Semantic memory, we have things such as semantic cache or knowledge base that have vector embeddings in them. Genetic memory, that's an interesting one. Human beings have DNA that have information stored within it that inform maybe our eye color, our hair color. LLMs have parametric memory, right? LLMs come out of the box with some understanding of the world, of our world. This is their form of genetic memory. Then you can have other stuff, associative memory is missing from here, but you have knowledge, you could actually implement knowledge graphs and use graph traversal, which MongoDB also has a capability of, to actually enable a knowledge graph feature. So, we've seen a lot of customers, when they're trying to solve this problem, adopt different databases, like loads of databases. They use a graph database, they use a vector database, they use an operational database. And one of the key things, and one of the key reasons why people use MongoDB is it gives you all of that in one database. And it does it in an intuitive way. So today, we started off with Prometheus, handing fire to man. And like I said, I'm not here to hand fire because I believe that that fire, we already have it. It's intelligence, and we're trying to just pass it on to AI systems. And hopefully, unlike Prometheus, we don't get punished by them. And that's the end. I will take any questions. Do we have any? It doesn't have to be a question. You can also make comments to what I've said. I'm open to hearing different opinions as well. Or maybe things that any approaches that you have taken to answer, to implement memory. Okay, here we go.
Hello. Thank you for the presentation. Do you have practical examples on what we showed today and implementing memory on AI?
Yes, that's a good question. So, I was meant to put some links in there, but if you look for the GitHub repository, and this is a personal project of mine, it's not an official MongoDB project, and search for a library, Memories. It's meant to be a funny name, but Memories, you would see some of the approaches that I just mentioned there being implemented in real time. We have the idea of using a database as a toolbox implemented there now. And that came about from the limitation of the tools you can give AI agents. So if you look at OpenAI's documentation, you can only give an AI agent or the LLM information of around 10 to 20 tools because of the context window. But when you use your database as a toolbox, a database like MongoDB that is based on JSON, and we know that OpenAI have the JSON schema, it becomes intuitive because what you can do is store your tools in MongoDB with vector embeddings and then retrieve the right tools based on the query or the context at the time. So you can have 100 tools in MongoDB and then retrieve just 2 tools just before you send your prompt to the LLM. So that is a way that, and that's in the Memories library. So that's MEMORIZZ.
Thank you.
And there are a bunch of there's a bunch of researchers that are working on this problem, like the AI ops that Jonathan mentioned. MemGPT is now an official company called Letter. Yeah. If you add me on LinkedIn, you can add me on LinkedIn as well, Richmond Alake. I will send I could send some papers.
Hello. On the presentation, you show that indeed the model itself can really benefit from memory. Now, I have 2 aspects that are not clear for me. One is the weight of each specific memory segment, and the second one is the life cycle of the specific segment, meaning that if we apply short-term memories, we inevitably end up with hallucinations or deviations from the initial path. But if we apply very strong weights on specific segment, we might end up with quote-unquote experiences for the model, hence bias. How do we balance this?
So the question he asked was, in the memory units, I didn't talk about how you balance the weights, essentially, the weights within the memory units. And the reason why I didn't talk about it, because there is no answer. It's all experimental, it's all research, right? So in the generative agents paper, they had 3 factors: recency, relevance, and importance. And they added like a weight factor to them. So you could, the approach I'm taking is looking at that paper and using the weights that they use and then running some evaluation, and you have to actually tune the weights to see what works. Because you're right, there can be problems if you give more importance to different factors that you're using to use as some form of like activation signal for memory units. So the non-answer to the question is there is no ideal approach. It's experimental until there becomes an ideal approach.
Thank you.
The light shines on, it's very bright. All right. Is that all the questions? Going once, going twice. Can I actually ask a favor? I need to show my mom what I do for my job. She understands AI, but she's like, Richmond, you're going to Greece. Why? To talk about AI. She didn't believe me, so are you guys comfortable with me taking a picture and sending it? I was going to video call her, but we'll save that for next year. So, you guys just got handed fire. Feel free to make any... I'm not a Gen Z. I don't know how to hold. I don't know how they do this. So let's see. Let's try this. Let's go. All right, guys. Look like you just had the most exciting talk. All right, thank you.